In our modern world, change often feels instantaneous. We have become accustomed to a rhythm of progress defined by the digital pulse of our civilization. An idea born in code, a simple string of logic crafted in a quiet room, can circle the globe in seconds, deployed to millions without friction. Software updates appear on our devices overnight, delivered silently while we sleep. These updates subtly, and sometimes profoundly, alter how we work, reshaping workflows and enabling new forms of collaboration. They alter how we communicate, collapsing distance and time. And they are beginning to alter how we perceive reality itself, layering information over our field of view. This is the world of the digital, a domain of pure information. It is a realm defined by its seeming lack of physical constraints, where concepts like mass, friction, and inertia feel like distant, archaic notions. It is a world of bits, bytes, where progress is measured in processing cycles and algorithmic efficiency. The core belief is that with enough ingenuity, any barrier can be optimized away. The prevailing narrative is one of accelerating speed, of exponential curves that defy gravity. It's a story of barriers dissolving in the face of pure information. This perception is especially strong, and perhaps most seductive, when we talk about artificial intelligence. AI appears to be a technology that evolves not in years, the traditional timescale of industrial progress, but in months, or even weeks. New models emerge with capabilities that eclipse their predecessors at a dizzying pace, rendering last year's state-of-the-art obsolete. This story of rapid, almost frictionless progress is compelling. It fuels investment, inspires innovation, and shapes our collective vision of the future. It is also incomplete, dangerously so, because beneath the surface of this digital revolution lies another world, a parallel reality that operates on an entirely different logic. It is a world made of concrete, steel, copper. It is the physical world of infrastructure, the silent, essential foundation upon which all digital activity depends. This is the world of atoms, not bits. This world operates on entirely different principles, and on a vastly, almost unrecognizably different timescale. It is a realm of mass and energy, geology and hydrology, manufacturing lead times and construction schedules. Unlike software, which can be copied and distributed at virtually no cost, physical systems must be built, atom by atom, ton by ton. Their creation is governed by the unyielding laws of physics, the constraints of global supply chains, and the complex, often contentious realities of human society, from zoning laws and environmental reviews to community consultations. The disconnect between these two worlds, the fast world of digital intelligence and the slow world of physical infrastructure, is becoming one of the most significant yet least discussed challenges of our time. It is a quiet crisis of mismatched timescales. We celebrate the speed of AI's development, marveling at its emergent abilities, while often overlooking the immense, slow-moving industrial base required to power it. We see the intelligence, but we are blind to the metabolism. Every query sent to an AI, no matter how trivial, every model trained, a process that can take weeks and consume megawatts of power, every insight generated consumes real energy, generated by real power plants, and requires real cooling, often involving millions of gallons of water, all delivered through a physical network that is staggeringly complex and geographically fixed. This network does not appear by magic. It cannot be downloaded or instantiated from the cloud. It is the product of long-term planning, of forecasting demand decades into an uncertain future. It requires massive capital investment, often billions of dollars committed years before a single watt of power is delivered. And meticulous engineering, balancing performance, cost, and resilience against the unforgiving realities of the physical world. These are processes all unfolding over periods that can span a decade or more, from initial concept to final commissioning. This documentary is an examination of that physical reality. It is a journey into the engine room of the 21st century, We will step away from the abstract realm of algorithms and neural networks and into the tangible world of power grids, water pipelines, and global supply chains for everything from copper to concrete to high-voltage transformers. Our focus will be on the systems and the processes that govern how the foundational layer of the digital age is actually built, maintained, and expanded. It is a story not of sudden breakthroughs, but of dependencies and constraints. It is a story of gradual, deliberate, and often delayed construction, where a single permit can take longer to secure than it takes to develop 3 generations of a software product. By exploring the cause and effect relationships that define infrastructure development, from land acquisition and regulatory approval to the finite capacity of the specialized workforce, we can begin to understand why the physical world cannot move at the speed of software. It is not a failure of will, but a function of physics and political economy. Understanding this fundamental mismatch is the critical first step in navigating the true challenges and opportunities that lie ahead for the future of artificial intelligence. The central paradox we will explore is simple, yet it defines the trajectory of our technological future. Artificial intelligence moves fast. Its progress is measured in months, driven by the iterative, abstract, and scalable nature of software. An algorithm can be rewritten overnight. A model's architecture can be refined in weeks. This is the world of bits, where the primary constraints are human ingenuity and computational power. But the physical infrastructure it requires does not. It is governed by the unyielding laws of physics, economics, and civil society. This is the world of atoms. While a new breakthrough AI model might be conceived, developed, and trained in a matter of months, the power plant needed to supply its enormous electricity demand can take 15 years from initial proposal to full operation. That decade and a half is consumed by years of environmental impact studies, protracted legal and regulatory approvals, complex financial arrangements, and finally, the immense logistical challenge of construction. This fundamental mismatch in timelines is not an accident or a temporary bottleneck that can be optimized away. It is an inherent, structural feature of building large, complex, and reliable physical systems in the modern world. Unlike software, which can be endlessly patched and updated, a concrete foundation, once poured, is effectively permanent. A mistake is not a bug. It is a multi-million-dollar, multi-year setback. The processes are slow by design, a deliberate methodology refined over generations of engineering practice. They are intended to manage immense risk, the financial risk to investors, the operational risk to national power grids, and above all, to ensure public and worker safety. These timelines also exist to balance the often competing interests of communities, who must live with the consequences of development, industries, which require reliable inputs to function, and the long-term health of the environment. Speed is often the enemy of stability when it comes to the foundational systems of our society. Rushing these processes doesn't just introduce error, it multiplies systemic risk. This documentary will adopt a calm and analytical frame to investigate this paradox. We will avoid the language of hype and fear that so often surrounds discussions of artificial intelligence, which tends to obscure more than it reveals. Instead, our approach will be grounded in systems thinking. We will look at the entire life cycle of AI infrastructure as a deeply interconnected system, from the mining of raw materials to the decommissioning of a facility decades later. We will demonstrate how a decision made in one area, often years in advance, has cascading and often irreversible effects on all others. For example, the choice of a data center's location is not just a simple real estate transaction. It is a decision that fundamentally impacts the local power grid, often requiring upgrades that themselves take years to plan and build. It affects regional water resources, competing with agriculture and residential needs for a finite supply. It reshapes the local labor market, creating demand for highly specialized construction and engineering trades, and it establishes a physical and economic presence in a community for decades to come, creating a permanent lock-in effect. Understanding these intricate, long-term connections is the key to grasping the true, unhyped pace of technological change. Our investigation is therefore relentlessly infrastructure-focused. We will not be debating the ethics or the ultimate potential of AI itself. That is a separate, important conversation. Instead, we will be examining the material world that makes it possible: the steel, the concrete, the copper, the water, and the energy. This means we will spend time understanding the unglamorous but critical details, like grid interconnection studies, which can take years to complete and determine if a new facility can even connect to the power network. We will explore the global supply chain for high-voltage transformers, massive custom-built devices with manufacturing lead times that can exceed 2 years. We will trace the sourcing of copper for cabling, a fundamental commodity whose availability is subject to geopolitical and market pressures, and we will unpack the legal and environmental challenges of securing water rights for cooling systems, a process that can be as contentious and lengthy as any other part of the project. These topics may seem technical or mundane, far removed from the exciting frontier of artificial intelligence, but they are the real-world, non-negotiable constraints that ultimately govern the growth of AI. They represent the precise point where abstract, exponential computational demand meets the unyielding, linear realities of the physical world. The purpose of this slow, explanatory pacing is to build a comprehensive understanding from the ground up, layer by layer. We will not present dramatic claims or offer simple, superficial solutions. Rather, we will gradually assemble a mosaic of evidence, drawing from the distinct but interlocking worlds of civil engineering, public finance, utility regulation, and global logistics. This methodical approach allows us to see the bigger picture, to appreciate not just that the timelines are long, but precisely they are so long. It allows us to recognize that these delays are not necessarily failures of the system, but are often the intended result of rational choices made by prudent regulators, cautious investors, and meticulous engineers to ensure that what we build is safe, reliable, and sustainable for generations. The goal is to provide a measured, evidence-based perspective on the physical limits to our digital ambitions and to understand the true material cost of intelligence. Our central claim is that building the large-scale infrastructure required to support a major AI cluster is a process that typically takes 10 to 15 years. This timeline is not an exaggeration. It is a conservative estimate. It is based on the standard sequential phases of development for any major industrial project. This journey begins long before any ground is broken. It starts with demand forecasting, utility planners, data center operators. Predicting energy needs a decade or more into the future. These forecasts trigger a long chain of events, planning where and how to build power and cooling capacity. The first major phase, planning, permitting. This is where the project meets society. Site selection, land acquisition, navigating a labyrinth of regulations, local regulations, state regulations, federal regulations, zoning approvals, environmental impact assessments, water access studies, community consultation, all governed by legally mandated timelines and public review periods, designed to be deliberate. Scrutiny, legal challenges, political debate, intentional friction to prevent costly mistakes. But years can pass before a shovel of dirt moves. Once permits are secured, engineering and procurement begin. Confronting global supply chains, building power infrastructure is not like ordering off a catalog. Large power transformers, high-voltage switchgear, backup generators, produced by a limited number of manufacturers worldwide. Lead times from months to years. A delay of a single critical component can halt a schedule. Supply chains for steel, copper, concrete also bottleneck. Finally, construction and integration. Massive logistical effort coordinating thousands of skilled workers. Electricians, pipe fitters, civil engineers, crane operators, building a substation, laying miles of high-voltage cable, constructing sophisticated cooling systems. Tasks that are complex, dangerous, sequential, and must be safe. Once built, the system must be rigorously tested and integrated with the grid. Commissioning can take many months, ensuring reliable operation without destabilizing the wider electrical system it depends on. Each of these phases adds years to the total project timeline. To understand why this 10 to 15-year timeline is the norm, we will break down the entire process into its core domains. This documentary will explore 8 interconnected areas: planning, regulation, power, cooling, supply chains, finance, workforce, geopolitics. By examining each one, we can see how they collectively create a system of slowdowns. Progress is governed by the slowest moving part. You cannot parallelize physical construction the way you parallelize software. Pouring concrete requires time to cure. Securing a permit requires a legal review period. Manufacturing a transformer takes a fixed amount of time. These are sequential, not parallel processes. Power, cooling. Modern power grids were designed for predictable, distributed loads. They are struggling with the sudden arrival of massive, concentrated AI data centers. There are multi-year queues for connecting to the grid. Building new transmission lines crosses public and private lands, a huge challenge. Cooling demands enormous water. Cooling demands enormous energy. Engineers face trade-offs: efficiency, cost, environmental impact. These constraints are rooted in physics and geography. Beyond engineering, finance, and supply chains, large projects require billions in capital. Investors prioritize stability, predictability, low risk. That demand for certainty drives years of due diligence, risk analysis, and financial structuring. Caution extends project timelines. Global supply chains show limited manufacturing capacity. They show geopolitical tensions. They introduce unpredictable, lengthy delays. Finally, the human and political dimensions. Skilled workforce availability sets a hard limit. Specialized engineers, certified electricians, training and certifying workers is slow. Infrastructure is embedded in geopolitics. Sourcing decisions get entangled in trade disputes and national security concerns. That adds another layer of delay. Look at the whole system of systems, and you see the gap between the speed of an idea and the slow, deliberate work of giving it a physical home. The journey to build the physical world for artificial intelligence begins not with bulldozers or blueprints, nor with the laying of fiber optic cables. It starts long before any ground is broken, in a domain far removed from the construction site. It begins with a quiet, deeply uncertain, and profoundly consequential exercise: forecasting the future. This is the invisible first step, a discipline of statistical modeling and educated guesswork that underpins the entire material reality of the digital age. Years, often more than a decade, before a data center is even a concept on a corporate roadmap, a diverse and often disconnected group of actors: utility planners, independent grid operators, government regulators, and large technology companies engage in the complex process of long-term demand forecasting. At its core, this process is an attempt to predict, with a reasonable degree of accuracy, how much electricity a specific region will need to power its homes, businesses, and industries. The time horizons are immense, stretching out 10 years, 20 years, sometimes even 30 years into the future. This long-range view is not an academic choice. It is a necessity dictated by the unyielding timelines of heavy infrastructure. These forecasts are the fundamental trigger for all major energy infrastructure investments. They are the documents that justify allocating billions of dollars in capital and committing to projects that will shape a region for generations. If the forecast indicates a significant and persistent gap between projected future demand and the existing, depreciating supply, it signals the need to begin the slow, arduous, and capital-intensive process of building new power plants, new high-voltage transmission lines, and new substations to deliver that power. Historically, these forecasts were built on a foundation of relatively predictable, slow-moving patterns. Planners analyzed demographic trends, like population growth, and tracked the pace of steady industrial and commercial expansion. A new housing development or a new factory would add a known, calculable load to the grid. This allowed for methodical, incremental, and long-range planning with a high degree of confidence. The system was designed for stability, not for speed. The sudden, explosive rise of artificial intelligence has shattered this century-old model of predictability. The energy appetite of a single large-scale AI data center, a facility that can be conceptualized and committed to in a matter of months, can be equivalent to that of a small city with hundreds of thousands of residents. Crucially, this enormous new demand can emerge in a fraction of the time it takes to permit, finance, and build the power infrastructure required to serve it. The timelines are fundamentally mismatched. This creates an unprecedented and deeply uncomfortable challenge for forecasters. They are now forced to account for a new variable in their models that is both massive in scale and highly volatile in its timing and location. This volatility is driven by the rapid and unpredictable pace of technological breakthroughs in machine learning. A new model architecture or training technique can suddenly render previous hardware obsolete, triggering a new wave of construction. This profound uncertainty forces planners to operate with a much wider margin of error, often modeling multiple divergent scenarios: a low-growth case, a high-growth case, and an extreme AI-driven step-change case. They must consider not only the potential for one massive data center, but the very real possibility of an entire cluster of them emerging in a single region, drawn by factors like favorable tax policy or access to fiber optic networks. This creates a highly concentrated electrical load that could overwhelm and destabilize the local grid, which was never designed for such intensity. To refine their models, forecasters now incorporate new, faster-moving data streams, tracking corporate investment plans, monitoring advancements in chip efficiency, and even analyzing public statements from tech executives. Yet for all this effort, the forecast remains an educated guess about a future that is being invented in real time. The variables are simply too numerous and too dynamic. A breakthrough in algorithmic efficiency, or a novel, more energy-efficient chip design, could dramatically alter consumption patterns, either upwards or downwards. Such a development could render a carefully constructed multi-year forecast obsolete overnight, adding another layer of profound financial and operational risk to the entire planning process. The consequences of an inaccurate forecast, in either direction, are immense. The stakes are no longer just economic. They are societal. Underestimating demand, the more immediate fear in the age of AI, can lead to power shortages, rolling blackouts, and widespread economic disruption as industries are forced to curtail operations. This forces grid operators into a reactive posture, scrambling for expensive and often carbon-intensive emergency power sources, like diesel generators, simply to keep the lights on. But overestimating demand is equally problematic. It can result in billions of dollars of investor and ratepayer capital being sunk into massive power plants and transmission lines that sit idle, underutilized for years. This is a stranded asset, a monument to a future that did not arrive, with the enormous costs ultimately socialized and passed on to all consumers through higher electricity bills. This is the precarious tightrope that utility planners and regulators must now walk, balancing the risk of blackouts against the risk of building expensive, unnecessary infrastructure. Their work, conducted in the quiet of an office and debated in regulatory hearings, sets in motion an irreversible chain of events that will lock in capital, land use patterns, water rights, and environmental outcomes for generations to come. It is a decision of immense gravity, all based on a decades-long gaze into an increasingly cloudy and turbulent future, a future being reshaped by the very intelligence this infrastructure is meant to power.